Sorry, I'm running a little late here. Okay, today we're going to move into the next section, law of cosines. And then I think we're going to have enough time because law of cosines, this section's really short. After law of cosines, I think we're going to start vectors. That's the plan. Did you have a good weekend? Okay, law of cosines, 9.3. I have some animations that I want to show you today, so that's why I'm using the projector. Law of cosines. Now, you remember the law of sines, right? That was pretty nice. We liked it. Let's motivate this idea with an example. All right, so let's start with a triangle. A is 2, B is 3, and angle C is 60 degrees. So remember that everything I'm doing in terms of the triangle I'm doing this off camera here, but A, B, C, little a, little b, little c. So we were basing all of this off of this triangle, right? And we had the law of sines from last class. Now, if we try and solve this triangle, that means figure out what capital A is, capital B, and little c is off of this. Can we do it with law of sines? Well, let's see. Can we get capital B? We don't have two angles, right? So we can't solve for a third. What can I do? Can I do anything here? What do you mean the hypotenuse?
I mean, you can make a right triangle and
Go right triangle here. Well, I'm saying using the law of sines. Let's say we were going after capital A. All right? If we were going to go after capital A, then we would use sine capital A over little a equals, then we would either have to use sine capital B over little b, or we'd have to use sine capital C over little c, right? One of those. So could I use this? Sine capital A, do we have little a? Yes, okay. Sine capital B, do I have capital B? No. Do I have little b? Yes, I have two unknowns here. I can't use that, right? Could I do CC? Like that? Same thing. I don't know. I know capital C, don't I? 60 degrees. But do I know little c? No, so I still have two unknowns here. So there are triangles. The whole point of this is that there are triangles where if you're given certain pieces of information, you cannot use the law of sines to solve the triangle.
And then you use that.
What's that?
And then cosines.
The law of cosines is going to cover this situation.
So
all right?
the majority of the time it's sine, and then the rest of the time it's cosine?
I wouldn't say it's one or the other, more one or the other. What I will say is that if you can use law of sines, use it. Because the law of cosines one is a more complicated formula.
Cosines work, use that, and then cosines.
That's right.
Cosines you cosine.
So let's actually come up with the formula, all right? I'm going to prove the law of cosines here. And I'm going to draw, to do it, I'm going to draw a picture. And I'm going to see if y'all can follow along with this. All right, this is the origin, all right, everyone? I'm going to draw a triangle. And this triangle is just some random triangle here, okay? I'm going to label this side little a, this side little b, and this side little c, which forces this to be angle A this to be angle capital C, and this angle to be capital B. All right? So there's a triangle. This is the origin, which means this is the point 0, 0. All right? Everyone okay with that? All right, now what I'm going to do is I'm going to construct a vertical line, which is, we call this dropping a perpendicular. I'm going to start from this vertex of the triangle. I'm going to drop straight down a line that would be perpendicular right here. Like that. Okay. Now, I would like to know right now, how long is this side right here, from here to that point right there? How long is that side? Well, what's the length from here, all the way from here to here? This is B, right? This is B. This side right here has a length. How can I get it? We could name it X. We could, but here's what I'd like for you to kind of visualize it as. Isn't this the X coordinate of this point?
Yes.
Okay. So what are the coordinates then of that point? If I were to ask you what is its coordinates?
There's no grad and no number line on there. Are you
Maybe I can.
term of a unit circle still?
Yeah. See, it's not a unit circle,
Okay.
but it's tied into this. When we were defining trig functions, do you remember when we defined trig functions like this? And we said the x coordinate would always be r cosine theta, and the y coordinate would be r sine theta. This is if we had an arbitrary line of length r. Now, if the r is 1, the unit circle, then it's just cosine theta, sine theta, right? But if it's not unit length here, right, then this is r cosine theta, r sine theta. Do y'all follow that? You remember that? Okay, so looking at this segment that goes from here to here, the r is actually a, isn't it? And then c is the angle, not theta. So this point, the x coordinate should be what? A cosine c, and the y coordinate should be a sine c. Yes? All right. Now back to this. If the length from here to here is b, and the length from here to here is what? What's the length from here to here then? It's a cosine c, right? It's the x coordinate of this point. So this is a cosine c. You following that? One more thing I want us to get. What is this length right here? B minus a cosine c. So isn't this length right here, that length take away that length? Okay, so this right here is b minus a cosine c. All right. Nice. This is looking like a catastrophe up here. Now, what else can we get here? Let's do it this way. Let me erase this. I want us to just focus our attention on this right triangle right there. Okay? Just that right triangle right there. Give me the Pythagorean equation or Pythagorean identity for that. What I mean is, give me a squared plus b squared equals c squared for that right triangle. So that would be this side squared plus this side squared is this side squared, right? I'm going to start with this. This squared, c squared, should be equal to what?
A squared, b squared?
this squared, right? This squared,
So B minus A cosine
b
C.
minus a cosine c squared plus a sine c. This one right here, that's this height, isn't it? This height right here is a sine c squared. Do you all agree with that? Okay. Now, believe it or not, our law of cosines is going to come from this right here. But I needed to get the setup of all the sides first. I drew an arbitrary triangle. Then I found this point by dropping the perpendicular. I was able to figure out the length of this. Here's b. This is b minus a cosine c. I know that this height is a sine c. It's the y coordinate of that point. So I've got my equation. Now, let's actually square that. All right, I'm going to square this and square this. So c squared equals, when I square this, I have to do like a FOIL, don't I?
Yeah.
And I'm not going to go through all the work. I'm just going to put the result. We should get b squared. Anyone know what the next piece is? Minus 2ab cosine c. Then what's the last piece of that? Plus a squared cosine squared c. That's just expanding this out. This times itself. Y'all buy that? That's what that would be? What do I still have at the end over here? Plus this squared, right? Isn't that a squared sine squared c? So notice my notation here. When I squared that last one, I squared the a and the cosine, right? When I squared this, I squared the a and the sine. So is that appropriate, okay? You follow that notation?
Say it again.
When I squared this,
Okay.
I squared the a and I squared the sine.
Yes.
Okay. The only other way I could write that is to leave it in parentheses. Okay? If I'm going to square it, since it's multiplication, I have to square each one of the factors. Okay. Now, does anyone see what can happen here? Almost 1. The a squared is a problem. So why don't we factor an a squared out of those? If I factor an a squared just out of these two, what will I have? I'm going to have to erase this. A squared, I'll be left with cosine squared c plus sine squared c. So this becomes 1. I agree with that, but what was still there? A squared, right? A squared? Okay. So here's where I am. I have that c squared equals what? I have b squared minus this, right? Plus what? A squared. So I have b squared minus this plus a squared. I'm going to write it a squared plus b squared minus this stuff. Just going to change the order. So c squared equals a squared plus b squared minus 2ab cosine of capital C. And that is the law of cosines. Now, let's try and appreciate what this equation does for us, all right? And to make us appreciate that, I'm going to draw a general triangle here again. So we have our C, little c, oops, B, capital A, little b. This is little c. So let's try and appreciate this. For the law of cosines, I can find little c, right, if I know A, B, and capital C, right? I need to know capital C, little a, and little b, and I can find little c. Agreed? So let me circle in red the things that I know. I know little a, right? I know little b, and I know capital C. So the way you can look at law of cosines is like this. If you're trying to solve a triangle where you have two sides of the triangle and the angle between the two sides, then you can use law of cosines.
SAS.
Side, angle, side.
So I keep remembering, I remember in our pre-cal high school, they were teaching us the acronyms SSA and SAS, but you can do
Yep.
SAS.
Yeah, so that was that. Remember when I talked about that? The book talks about angle, side, angle, side, angle, side, and that I don't really approach it that way. I just don't. But yeah, if you remember that, that's most likely.
Sine is Lowe's law of cosines.
It all. I like to look at it from the perspective of you understanding what you have in the formulas and how you use them, as opposed to if I have side, angle, side, I will apply law of cosine. You know, it's less robotic. I'm not saying that's the way you do it. I'm just saying
Well, that's just what I remember.
that's if you remember. Okay, that's your law of cosines. All right. Now, when I drew that triangle initially, right? When I drew the first triangle, I picked what I called A, B, and C, didn't I? I picked the sides. So it turns out that if I drew that triangle again, but I changed two of the sides, I would have another formula that would look just like this, but it would be this instead. It would be B squared equals, you tell me,
A squared plus C squared.
A squared plus C squared minus
AC
2AC, that's an A, C cosine
of B.
capital B.
Capital.
All right? So that's an equivalent formula. They're all the same formula. You have two sides in the angle between them. You use this. It's just, it depends on what you label A, B, and C. So the last one is A squared equals B squared plus C squared minus 2BC cosine of capital A. Those are the law of cosines that you'll find in a book, those three. Now, sometimes you're given all three sides of a triangle and no angles, which would be side, 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 right? But we can use these formulas, just rearrange them to be able to get new formulas. So let's see, could I get the C, the capital C by itself?
Isn't it attached to the argument of the cosine?
Pardon?
Isn't it attached?
It's attached, right? But
That's the argument of cosine.
yes, it's the argument of cosine. I can't take the C out, but let me try and get this by itself. So let me move the A squared and B squared to the other side on this first equation. So I'm going to have C squared minus A squared minus B squared, right? That would be these two to this side, yes? Then let me divide out negative 2AB. If I divide out negative 2AB, wouldn't I be left on the other side with cosine capital C,
You sure would.
right?
Therefore, allowing you to solve for triple sine.
What?
Therefore, that allows you to solve for triple sine.
If I know all the sides, A, B, and C, right, then I can get this number.
And then you can get an angle.
And then I can get cosine of something is a number, and then I can use my calculator to do arc cosine. All right?
And then when you have one side, you can solve for the rest. Well, I mean, when you have one angle, you can solve for the rest. Because then you can
Well,
the formulas.
if you have one angle, you won't be able to get the other two, but you can do it again. Or you can use law of sines to get the other angle.
So
Yeah,
once you get one angle and three sides, you can solve for the rest.
that's right. We'll do an example. Now, you won't see this in the book like this, okay? It's going to be a little different. What they do, remember on negative signs, if you have a negative in front of a fraction, here's a fraction. If you have a negative in front of a fraction, the negative can go on top or on the bottom or out front. So if I put this negative out to the front, then push it up through the top, it will change the signs on the top, won't it?
Yep.
And so I can rewrite this as A squared plus B squared minus C squared over 2AB equals cosine capital C. All that's happened here is all the signs on the top changed, all the signs on the bottom changed, and I rearranged them. You will see that in a book, all right?
It looks better.
It's just
Does
the
book do
signs.
that automatically for you? It factors that negative to the top?
I actually don't know. And I might be lying to you. The book might not have, oh, the book doesn't have it, sorry. This book does not have that formula.
That's just going to make it easier to solve, right? Just-
Yeah, so do you remember when we had law of sines? I said if you're looking for the angle, do like sine A over little a. But if you're looking for the side, do little a over sine A. Remember that?
Yes.
Okay, this would be, with law of cosines, I would say, look, if you're trying to find an angle, use this version. If you're trying to find the side, use this version. All right? So there's, yeah, whatever you're have isolated, dictates which formula you're going to use. Now, do you see that there's two other formulas for this also?
Yes.
If I went and solved those, I'm not going to, but do you see? Okay, let's go back to that original problem that I put on the board. A was 2, I think. B was 3. And angle C was 60 degrees. Double check that. Yes. Okay. So I can't find, I can't use law of sines on this, right? I showed that when we set up the ratios, we had 2 unknowns no matter how we did it. So we have capital C, right? Look, this formula has capital C. All I need is little a and little b to use it, right? And I have little a and little b. So I can solve for little c now, can't I?
Yeah.
Okay, let's do it. Little c squared is equal to a squared, which is 2 squared, plus b squared, which is 3 squared, minus 2 times a, which is 2, times b, which is 3, times cosine of 60 degrees. So that's just me plugging in a, b, and capital C into that formula. C squared equals 4 plus 9 minus, what do we have here, 12. What is cosine of 60 degrees? It's the x-coordinate at 60 degrees.
0.5.
Half?
Yeah.
Okay, so half.
Minus 6. So 13 minus 6.
13, take away 6 is
7.
7. Okay.
Root 7.
Root 7. We're going to have to do plus or minus,
Plus or minus.
right? Because we are going to take a square root. So c squared equals 7, which means c is equal to plus or minus root 7. But c is the length of a side of a triangle.
So it's positive.
So it's got to be the plus. C equals root 7.
And now that you have that, you can use law of sines to do the rest.
Yeah, if we want to continue the rest of the triangle, now we have little c.
Yeah, I'm remembering that stuff. That section we did mess with now. Because we did it the other way. Because we did it the other way.
You're like at total different extremes. You're either like asleep or like, wah!
And it ends in my minutes.
Okay, all right.
But I just remember in high school the way we did it was the side angle side or whatever. Since we did it that way, like the entire test for that section.
Okay,
was just
Zach.
one
All right,
line.
Zach. Okay, that's enough. I appreciate the feedback, but all right, let's go find, what do you want? Capital A? Capital A. All right, sine capital A over little a, and then I can use, what do I need to use? I don't really have a choice here. Capital C? So 60 over root 7. That's what I'm going to use. Oh, and I should have replaced little a with 2. All right, so you see how I have 3 of the 4 pieces now? And then I can go get this. So sine of capital A is, sine 60 is root 3 over 2, isn't it? But really, it's probably calculator time at this point. Did I leave my calculator? Darn it, I had it on my desk. Oh, you can, no, y'all can do it. I trust your answers. This is sine A equals, it's going to turn out to be root 3 over root 7. Because that's root 3 over 2 times 2. The 2's cancel, so root 3 over root 7. Who has that? Sine A is what? 0.654? 0.655? Okay, now at this point, what do we do? Arc sine. So when you do arc sine, let's make sure we're in degree mode because this was in degrees. So what do you get for your angle?
40.91.
So A is 40.9, what? 2 degrees? All right, we always have to be a little careful here because remember arc sine, there was restrictions on the domain and all that stuff. 40 degrees on the unit circle means that you were somewhere around here, right?
Where do you get the root 3 from there for the sine A equals root 3 over?
Sine of 60 degrees is root 3 over 2. And then I canceled the 2's.
You got it from the unit circle.
Yeah, I just went off because it's a nice angle. If not, I just would have typed it in the calculator and eventually got to 0.655. So we're saying that our angle needs to be 40.92 degrees. And that's because this number right here is the y coordinate. Agreed? Is there somewhere else where we could also have that happen? Over here, right? Now, what would that angle be? This is 40.92 degrees. This would be 180 minus 40.92. What is it? 139.08 degrees? So should we consider this?
Yes.
We should consider it, and then don't consider it. Why? Because angle C is 60, right? And the sum of all the angles has to be 180. So it's impossible for this to be 139 because angle C was 60. You're already past 180. Question?
Now I was wondering where we get the 40.92 from. Sorry.
Arc sine of 0.65. So we throw out that 139, but we want to make sure we throw it out. I mean, we have to consider it because we saw last class you could possibly have two triangles that do this. So now I know what capital A is. Capital A is 40.92 degrees. And then the last thing to get is capital B, but that I can get by just adding these up, subtracting it from 180. So what is 60 plus 40? And it's basically what, 79.08?
Yeah.
79.08 degrees just by doing some arithmetic with those two angles. Is that clear? So law of cosines came into play. It was there just to figure out what little c was. Once we got to little c, went back to law of sines. Questions? I want to do something a little bit different. You saw how we did that problem, right? Okay. I want to go back to the place where we had figured out what A, B, and C were, okay? Before we went and found capital A, all right? We use law of sines, we're in business. But what if we had used the law of cosines instead? What I mean is you could do the law of cosines. What am I looking for here? Capital A? There is a formula, law of cosines, that would be what? So look back in your formulas. There was a formula that we had. It was a squared equals b squared plus c squared minus 2bc cosine of capital A, right? That formula? If we solve this for cosine of capital A, we would basically move these over, divide by negative 2bc, and then switch the signs, and we would wind up with something that looked like b squared plus c squared minus a squared over 2bc, right? I could have used that formula to get capital A, and I want to do it because I want you to see something. So if I use this, cosine of capital A, I'm going to do b squared, which is 9, plus c squared, which is what? 7, right? Because we're doing root 7 times root 7 is just 7. And then minus a squared, which would be minus 4, over 2 times b, which is 3, times root 7. And I'm going to need someone to go ahead and figure out what that is for me. I know the top is 312, right, over 6 root 7. So if you could, please, someone give me 12 over 6 root 7.
15.87.
What is it?
15.87.
I think your parentheses. You have to do 12, and these two have to be in parentheses, like when you do your divide.
The 12 on the bottom.
Oh, you did the bottom. Okay, so sorry, the 12 over that part. you shouldn't. The number's got to be between 0 and 1, or between -1 and 1. 0.12? 0.75? I'm getting more 0.75s. 0.76? You got something different? What? You're not happy with 0.75?
0.756.
12 divided by this.
Yep.
Let me see the way you type that.
Yeah, when you round the 5.
0.75. Let me see. Oh, you did 2, not 12. You see it?
Yeah.
Chemistry.
Okay. Okay, so 0.75, 0.76, fine, whatever. All right, to get capital A now, arc cosine. Do arc cosine right now. And what do you get? Arc cosine of 0.75, and what do you have? 40.89. That look familiar? It's a little off, isn't it? Because we've had some rounding here. Oh, 41?
Yeah, 41.
All right. Look, let's just go with this. Pretty damn close to 41, right? This is rounding. These are rounding errors. So, look, here's what I want you to think about. This is the whole reason I did this, all right? When we did arc sine, at this point we had to go back and look at the possibility of having a different solution, didn't we? Do we have to do the same thing for cosine? When we do arc cosine, you have to remember when we do arc sine, the computer is not allowed to look in quadrants 2 and 3, right? It can only give us an answer that came out of the first quadrant. In addition to that, we know that our angle can't be in the fourth quadrant because the angle has to be less than 180. I mean, all the angles added together are 180, right? So it can't be possible to get an answer out down here. That's when we're doing arc sine. So what happens is we have to go look in the second quadrant because we might have an angle over there. But when you do arc cosine, where does it look at? Where does the computer looking at? The top two. Which means that the answer you get, there is no other answer that could exist. You don't have to go check another answer at all. There's only one. And so the computation, I think, is a little more... I think this computation might lead to maybe some errors with maybe you'll mess up a squared or something. But the good thing about using the law of cosines to get the angle is that you don't have to go check two different scenarios. Does that make sense?
Like in the law of sine.
Law of sines, you have to. So just be careful with that and use that if you like. It's just harder to remember the formula also, right? I mean, it's more complicated. All right, let's move on. Okay, the next one I want to do is this problem. Let's say that you have a track, a circular track. Right, so this is a perfect circle, it's a track. And let's say that you've got a runner, so we're looking from the top. You've got a runner who's running around this track in a counterclockwise direction like this, all right? And let's say that you have this, here's the center. You have this person who is watching this person run around the track. The coach, or just some pervert, I guess, watching someone run around a track. I don't know. It's got a person observing a person running around a track, okay? I'm going to give you a couple of pieces of information. First of all, the track has a radius of 400 feet. That's a pretty big track. And then I'm going to say that the distance from the observer to the center of the track is 1,200 feet. Okay? Now, I would like to know if let's say that the starting point for this person is right here. If they have moved around this track from the starting position, if they've moved, that looks more like 72 degrees. How far away are they from the observer? So how far are these two people away from each other right now? Okay. Yeah, I've got a green right there. So my question to you is, what's x? Find x. All right. No, we're going to work this one out. Okay? We're going to work this one out.
Well, the length from the center of the circle to the runner is 400 feet, so we already know that.
Okay, so you know from here to here is 400, right? So you got two sides and an angle, right?
400, 1600.
Do you know, is this angle between the two sides that you know?
Yes.
Yes, so we should be thinking law of cosines here. Because you've got this angle that's between these two sides. This is 1,200. So let's start labeling some things. Let's call this angle over here capital A, which makes 400 little a, right? Let's make angle 72 here. Let's make that capital B, which makes x little b, right? X is little b. And then this angle up here, C, corresponds to this little c, which is 1,200. I'm just trying to get you to see the whole triangle there, right? And what are we trying to find? X, which is really little b. I'm trying to use the same letters that are in the formula to keep this clean. So if I want to know little b squared is little a squared plus little c squared minus 2 little a little c cosine of capital B. We better know little a, we better know little c, and we better know the angle between them, right? Which we do. So now, this becomes b squared equals a squared, which is 400 squared, plus c squared, which is 1,200 squared, minus 2 times 400 times 1,200 cosine of 72 degrees. So go ahead and calculate that all out. And tell me what b squared is. Don't take the square root yet.
Squared is 1,303,000.
1,303,343.685.
343.685.
And we'll just see if at least one other person agrees with that. Not that I don't trust you. But it's always good to have verification.
Yes.
You got the same thing? Okay. Everyone understand? This is just arithmetic, right, on your calculator. Make sure you're in degree mode on your calculator. And now take the square root. So when you take the square root, and we're only going to look at the positive answer, you get what?
1,141.64.
1,000, what?
141.
400. 40,
141.
1,000.
1141.
Hold on. Oh, yeah, okay, never mind. 1,141.64. 6.4. All right. Feet, right? I didn't say the units here, but it's feet. Does that seem okay?
Yeah.
Okay. All right, now what I'm going to do is I'm going to bring up a problem from my Cal 1 class. All right? Not that we're going to do it, but I want you to see how, when you transition from pre-Cal into Cal 1, what we expect that you can do now that you've seen this. All right? So I'm going to erase this. I guess what I want you to notice right now is that you can solve a triangle, right? Pretty much, if someone gives you a triangle, if you have 3 pieces of information, you're good to go. I mean, you can pretty much figure it out, except if you get 3 angles. If someone gives you 3 angles, you can never really be sure about the triangle.
Also,
Right,
if you
it's-
angle side to side.
If you have like a right triangle, if this is 30, 30, 60, and 90, there's an infinite number of triangles that have those proportions or those angle proportions. So it's not enough information. You'd have to have something else. But that's aside from what I'm trying to show you here. Okay, so here we go. I'm going to present the problem and see what you think. A runner sprints around a circular track which has a radius of 50 meters. She runs at a constant rate of 7 meters per second. Her friend, okay, so not a stranger, not a weirdo, her friend is standing at a point 100 meters from the center of the track. Seem pretty reasonable, like from what I've given you in that previous problem? Seems pretty much in line. Although I did give how fast she's running, which is a little different, right? She's in motion, as opposed to the problem where I gave you, where I said when that runner was 72 degrees, how far away were they, right? This piece of information was not needed to answer our question, right? How fast the person was running, right? Was not relevant to us. Okay, look at the question. How fast is the distance between the two changing when the two are exactly 120 meters apart? Okay. First thing we need to do is try and see if we can't get a grip on what's happening here. Okay. You've got this person running around the track at a constant speed. You have a person observing them, right? What we're looking at here, this question is asking, at a certain instant in time, when they are exactly 120 meters apart, how fast are they moving away from one another? So imagine that as this person's running around the track, they're holding a rope that's tied to the person who's watching them. Then as they run around the track, they're going to have to let rope out, right? As they go around, and then as they go around, they're going to have to start letting rope back in, right? Pulling in. So you could look at that as the distance, this green thing right here, is constantly changing, isn't it? But is it always changing at the same rate? So think about right here. If this runner moves just a little bit, does that green change that much? If I move, let's say, from here to there, the rope's length changes, but not by much, right? Compare that to if it was right here to here. It changes a lot more, doesn't it? So from here to here, oh, come on, move. All right, there we go. From there to there, I have it calculated here. Look, it's 149, can y'all read that? It's about 149.76 meters between the two of them. If I move by that much, then it's like a 148.7, right? Didn't change by much. But if I go from Here, the distance is 112, but if I go from here to here, look, it went all the way down to 98. So in the same little segment of time, because wouldn't it take the runner the same amount of time to run this as it would this? Because they're running the same speed. So from here to here, the rate at which the distance is changing is small. From here to here, the rate at which the distance is changing is big. So the question is asking, at exactly that moment right there, when this distance is 120 meters, at that exact moment, how fast is that green thing coming out of your hand? Is the rope coming out of your hand really fast, or is it slow? What's the exact rate that it's coming out? Now, you can't answer this question without learning some more calculus. But to set the problem up, you must be able to draw triangles and use things that we're learning here. All right, so let me show you how this problem is set up, all right, to give you, I guess, a glimpse into the future, all right? All right, so the way we do problems like this, which if you want to know, these are called related rate problems, and students always love related rate problems, right, Diego? No? Is that the worst part of Cal 1, you think?
No, probably
Optimization? Yeah, okay. But it's right there, probably number 2? Huh? Okay, yeah, I guess so. Okay. Number 3 then, maybe. There's like 40 things on the list of bad things, right? No. Okay, so look, here's how we do a problem like this, a related rate problem. Because everything is in motion, you must first draw a picture of this situation where nothing is fixed. In other words, right now, at the moment they're asking, I can say that's 120, right? Because the question asks, at exactly the moment that they're 120 meters apart, how fast is the distance changing? You are not allowed to fix that yet. You cannot fix it at 120. You have to draw the picture as if everything is in motion. So, let me try and draw this. I have a triangle that looks like this. I know that that must always be 100, right?
Yeah.
That's not a right triangle, by the way. This has got to be 50 the whole time. That never changes, right? That is always the same in my problem. I'm trying to figure out what this is. That does change, doesn't it? X does change. And the only other thing that I know about is what? What else is changing?
You know the distance, you know the speed of travel.
The speed of travel around it. And what was it again? 7 meters per second. That's the linear speed of the runner. But I need something that goes in my triangle. This has to help me within my triangle. And so there's one thing that's also changing in this triangle that I can label, and that's the angle theta. That angle, right, changes as the runner moves. So if I'm given a linear speed, can't I change that into an angular speed?
Yes.
We did that in the very beginning of class, beginning of the semester. So let's see if we can't figure out the angular speed of this runner. So 7 meters per second, what is the circumference? What is the circumference of this circle? The circumference is 2 pi times r. What's the radius? 50. So this is 100 pi. That's the circumference, yes?
Yes.
Okay, how long is it going, how should I say this? Yeah, how long is it going to take for this person to go around one time?
300. Is it so it'll be
This is about 314.15.
Almost 45 seconds.
Almost 40. So how'd you get that? This is the meters, right? This is the distance around. Divided by 7. Okay, so take this number divided by 7, and that's going to give you what?
44.88.
44.8
8.
seconds, right?
Yes.
Is how long it will take this runner to go around one time. Yes?
Yes.
Now, angular speed is the angle over the time. That's your omega. You have to go back to the past, right? So the angle that I travel through is 2 pi, isn't it? I go 2 pi, and how long does it take me to go 2 pi? 44.8 seconds. So do 2 pi divided by 48.8 seconds, and you're going to get your angular speed. What do you get? 0.14? Yeah. 0.14 radians per second. All right. I know the rate at which this angle is changing, don't I? The rate at which it's changing is 0.14 radians per second. What I want to know is how fast x is changing, right? So I need to somehow come up with the relationship between theta and x. Can you think of any equation out there, anything you can come up with that relates x and theta together?
Opposite over hypotenuse.
If it's a right triangle. It's not a right triangle, though. Anything that would relate the angle between two sides we know. Law of sines,
Law of cosines, right?
but we have two sides, the angle between them, right?
Side, angle, side.
Law of cosines. Law of cosines relates these variables together, doesn't it? So in calculus, what you have to do is you have to draw a picture of the general scenario, and then you have to find an equation that connects the variables that you're interested in together. And in this case, it would be law of cosines. So I would be able to write down here x squared equals 50 squared plus 100 squared minus 2 times 50 times 100. And then cosine of what? Theta. That's it, theta. No, this right here is not theta. This is how fast theta is changing, right? Now, look, I've led you way out on a ledge here. You don't have any of the calculus tools yet. What I'm trying to get you to see is that before you can even do calculus, you have to be able to visualize this scenario, draw a picture, come up with an equation that relates these together, and then you do the calculus after that. All right? But there's no class that you're going to take, or we're not going to do anything in this class that's special that's going to get you ready for this. When you walk into Cal 1, you've seen law of cosines. So when I draw this picture on the board, you got to know that that comes from law of cosines, right? So, all right, that's a nice problem. I don't know, I may have. I don't remember. See, in calculus, the big difference, I don't think I've ever talked about calculus, have I, in here too much? The difference between every math class that you've taken up to this point, assuming you have not taken calculus, the difference between college algebra, pre-calculus, and anything else is that in calculus what you're doing is, let me say it this way. In algebra, pre-calculus, all the operations we do are finite. We do a calculation, work through it, it's over, right? We do a computation, it's over. In calculus, what we do it's the first time we do infinite processes. We do calculations that are infinite. We allow things to move as opposed to everything being static. And because of that, it becomes a little bit problematic. But you can't you can't land like people on the moon without being able to talk about motion and things that are moving. And would y'all like to see, while I've got this up here, would y'all like to see a couple of the types of problems that you see? I mean, why not, right? Okay, so, and we'll just talk about them just so you can see them.
This is all from your calculus class?
Yep. All my calculus class, I have all my notes are electronic. I have them all pre-made. I don't have that for pre-cal yet. Sorry.
Does that make it easier, the students say?
I don't think so.
So What's your schedule like for next semester for Cal?
I am teaching a Cal 1, I just don't remember when.
So you only have one.
It's only one.
It's at 9 a.m.
9 a.m.? Yeah, that wasn't my choice, I had to.
Is it Monday or Tuesday? It's
I think it's Monday?
Oh, yeah, Monday. I think I'll sign up for that.
Okay, so here, okay, this is one that you can visualize, I think. You have a person on the ground. You have a person on the ground, and you have a plane flying at a constant altitude overhead. All right, so you see the plane is flying, person's on the ground. And the question in this problem is that at a specific instant, like right there, how fast were they moving apart from one another? Because it's not always the same, just like on the runner on the track, it's not always the same. If you were to have to set this problem up, what geometry do you think you would be using? Right triangle, right? The right triangle. Okay, this next problem here is the same situation, plane flying overhead, but instead of saying at a specific instant, right there, not how fast were they moving, but how fast was this turning?
How fast were you turning your head?
How fast are you turning your head to keep up with that? So I like to give the analogy, if you've ever like stood on a road or like a train station or something. I'd never stood on a train station, but if you stand there and you're watching a train come, just imagine watching a train or a car come. Initially, you know, your head's turning slow, but as they get closer, it's like, yeah, right? You have to, in this portion, you have to turn your head very fast, but as they get further away, it's a slower rotation. And that's what this problem is doing. Trying to figure out a specific instant in time how fast something is changing. This one is a person, this is a light pole. This is a person that's 6 feet tall that's running away from the light pole. And we're trying to figure out how fast their shadow is moving. You see their shadow here?
Yeah, growing.
As they get further away, their shadow gets longer, right? So what we ask is at a certain instant in time, how fast is the tip of that shadow moving? Is it moving the same speed as the runner?
No, it's slow.
Yeah, well, we can argue about what it's doing. Calculus will give us the answer.
I believe it's speeding up.
I believe that problem turns out to be constant, which is not intuitive. The speed of the shadow is constant. The tip of the shadow moving. It's weird. This one, I like this one. Okay, this one is you're filling a cup, a funnel, right? You're filling it up. You're pumping a liquid into this at a constant rate. So if it's going in at a constant rate, in the very beginning, as it's filling up this portion, it's going to start coming up very fast, right? Because it's very narrow down here. But as you get to the top, it's spread out, so it slows down, doesn't it, as it comes up? So the question here would be, at exactly some instant, let's say right there, how fast is it coming up? Slow here, right? The further up you go, the slower it gets. Right? But right there, how fast was it moving? A lot faster than up here. And that's what you would be able to answer in that calculus class. How quickly is it moving up? I better stop that.
I wonder what's going on up there.
And then this was the runner around the track. Oh, this is a classic example. Where is it? This is a classic Cal 1 problem. You have a ladder that slips. Here's a wall. Here's a ladder. The ladder is moving out, and you want to know if this edge is coming out at a certain speed, how fast is this point coming down the wall? Are there any computer science majors in here? CS?
There is, but
He was. This is, how many of you've all seen Wolfram Alpha, right?
Oh, yeah.
Okay. So Wolfram Alpha, the company Wolfram makes a computer program called Mathematica, which is really the brains behind Wolfram Alpha, like all the computations. So this is the program. I have, on this computer, I have Wolfram